My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 640. In this lecture, we will try to understand training RNN's backpropagation over time. We have seen the structure of simple RNN in the previous lecture, but how does backpropagation works now? So the backpropagation that is used in training RNNs is called backprop over time. It's actually not a very hard concept since we know the backpropagation very well. Backpropagation over time is careful modification of this. Let's draw a diagram first. You have your xi1 here. Just observe this one. Of course, input to this is O0. O0 is basically zeros or random values. I have my O1 here. Just observe here. And I have my xi2 here, and all these are my f's functions. Actually, these are my activation. I can say these are my activation units, isn't it? Functions means what? Activation units. So if so on and so forth, what will you get here? I have xi1, xi2, xi3, xi4, so on. I can say xi9, isn't it? O8, just observe this one. What is here? O8. I have O8 as an input, the same function f, and it generates output. I can say O9. Let me say it is generating an output O9, and I have one more layer which takes I can say xi10, and same function it generates. I can say this function is generating O10. Let's assume my xi. What is my xi? My input xi1, my xi1, xi2, so on, xi10, my O10. I will take I will take it up here, and I have softmax layer, SM. Here SM means what? Softmax layer, which creates my yi cap. I have my weights here, W. I can say I have my weights here, W's. I have weight W dash. I have weights W dash, and also I have weights W double dash. And this is time axis. This is one layer. This is one layer representing itself over time. When I have my yi cap, I have loss function also, which takes yi and yi cap. My loss function L is yi of yi cap. Oh, our example problem is what it is. It is binary classification problem. I can use log loss, simple binary law. I can say it's a simple binary log loss, isn't it? Now let's look at calculus part of it. My O1 is, just observe what is my O1 here. Yes, this is my O1. How am I calculating O1? F function of W of xi1. This is W xi1 plus W dash of O0. This is W dash of O0. Similarly, just observe this one. Similarly, I can calculate O2. Just see, this is my O2. In similar manner, I can calculate O2, O3, so on, O4, so on, so forth, O10. That's similar logic, isn't it? My yi cap, let's assume my softmax is G. Let's assume my softmax function is G. In that case, my yi cap. What is my yi cap? Yi cap is nothing but, just observe this one carefully. This is G of, this is G. G is my softmax function. What is W dash into O10? This is G of, that is yi cap. Now how does the calculation work here? Let's look at the forward propagation. First, let's look at the forward propagation, then we look at the backward propagation. Very, very simple notation to understand this very easily. The direction of your arrows or forward direction in time is the way your forward propagation works. Just see, when you are performing forward propagation, what happens? Just see, your forward propagation works. Your forward propagation literally works like this. What I have written here is forward propagation. The sequence of steps O1. First, what we calculated O1, then we calculated O2, then we calculated O3, so on and so forth. This is forward propagation, and when you are performing forward propagation, W dash and double dash are same. That's important, isn't it? Weights only change. When weights only change, this point is important. Weights only change in back propagation. So forward propagation, just use the direction of arrows. That's why this notation of representing is very powerful. You can just follow the direction of arrows. These are your forward propagation arrows at time step 1. This happens. What is that? We can calculate at time step 1. We can calculate O1 at time step 2. We can calculate O2 at time step 10. We can calculate O10. You get, once you get this class label yi cap, your loss function. Now what about your loss function? We already discussed what is loss function. Now what about propagation? Once if you have loss function, what about your propagation? Forward propagation in the forward direction. Now what about back propagation? My backward propagation is opposite direction of your arrows. Actually very, very simple. So you have your loss function here. I can compute the derivative. I can compute, just see, when you are performing forward propagation, W's, W dash and W double dash are same. Weights only change in backward propagation, isn't it? L means what? What is my L? L is loss function. So you have your loss function here. So I can compute the derivative of this loss function with respect to yi cap. So first thing I will do is dou L by dou yi cap. Now if I get this, I can compute the derivative of my loss function with respect to output O10. Dou L by dou O10 equal to dou L by dou yi cap by dou O10. Because look at my yi cap depends on O10. That's important. My yi cap is function of O10. So I can compute the derivative of this with respect to O10 by just chain rule. Just try to recall what we discussed in backward propagation algorithm in few lectures back. We discussed for in the context of multi-layer perceptrons, isn't it? I wanted to modify, just see, I wanted to modify W double dash. Dou L by dou W dash is essentially dou L by dou yi cap and dou yi cap by dou W dash. My yi cap depends on both O10. My yi cap depends on both O10 and W double dash, isn't it? I'm back propagating over time. That's why RNN back propagation. That's why RNN back propagation is called back propagation over time, because this arrows is in forward direction. Just you have to reverse them, isn't it? In similar manner, I can calculate dou L by dou W. It is dou L by dou L is function of y. L depends on yi cap depends on O10. O10 depends on W. Now you modify. You modify W. Similarly, you can write it for W dash also. So when you are going forward, we went in the direction of arrows. While coming back, we will come in exactly opposite direction, isn't it? First we will modify these W's, then whatever modifications we are coming back over time, this is called back propagation over time. It is very simple concept. You literally have three metrics: W, W dash, W double dash in your memory. first you modify w, this is based on the derivative you get here, and then you modify the same thing again with respect to next step, so on and so forth. At the end of it, you will reach here. Just see, you update all these weights, w dash, w double dash with respect to one data point x1 y1, isn't it? When you reach here, you actually, if you have to modify like this, you are coming in reverse direction. If I speak strictly, you are coming this in this way, isn't it? After few stages you will come here, isn't it? When you are reach here, you are back propagated your weights and your weights, and you update all these three matrices. Which three matrices? W dash and w double dash with respect to one data point, that is x1 y1. Till now you only processed one data point, you repeat next data point, so on so forth. Your back propagation happens over time, isn't it? There is a problem with this simplest way to remember. This is to follow the direction of arrows. If I follow direction of arrows, you get forward propagation. If you follow the direction backward, you will get backward propagation. But backward propagation happens over time. These are not, that's important. Backward propagation, if you follow the direction arrows, you will get forward propagation. If you follow the direction backward, you will get backward propagation over time. These are not, these are, just see, this backward propagation happens over time. Just see, this is just, if you observe carefully, just see, if I used to get, if you these are not different w's, all these are same w's. These are not lot of people get confused. I used to get confused when I first learned RNNs. This is same w, we are using same w, everything happens over time. It is not multiple layers, it is just one layer. Having said that, there is one problem with this. Look at these weights. Just if you observe that these weights that you modified, you have 10 words, xi1, xi2, xi3, so on, xi10. Your derivatives of L means what? L means loss function with respect to w is, if you this dou L by w, dou L by dou w is a part of lots of other partial derivatives, because you have to follow this whole path backwards. When you come to the end of it, when you come to the first word, when you come in the reverse direction, when you come to the first word, this weight w, that we have modified for the first word, dou L by dou w. If I say dou L by dou w, lots of dou L by dou w, derivative of loss function with respect to first word, we have lots of multiplications of other. It is a part of lots of, I can say, lots of multiplication of derivatives less than 1. That's important. We have lots of multiplications of other partial derivatives. If you recall our multi-layer perceptron chapter, we realized that you have lots of multiplications and most of the values are less than 1. All of them are less than 1. Actually, we can just try to recall, we can easily run into the vanishing gradient problem. That's important. You can run into the vanishing gradient problem. You run into the vanishing gradient problem not because you have many layers, but you are repeating. Here problem is, if you have here issue is your vanishing gradient problem. Otherwise, let me repeat, you run into the vanishing gradient problem not because you have many layers, but you are repeating this operation over time. Imagine if you have a sentence which has, let's say 100 words. So you literally have 100 multiplications of partial derivatives and your activation units. Let's assume your activation function is sigmoid, or I can say tan h. Then all the derivatives are less than 1. When you multiply, vanishing gradient problem keeps in very, very fast. You can also have You can also have, if your partial derivatives are less than 1, then you have vanishing gradient problem. If partial derivatives are greater than 1, you will have a problem of exploding gradient problem, which we discussed in multi-layer perceptron. At the end of the day, you are multiplying lots of partial derivatives. If they are less than 1, then you have vanishing gradient problem. If they are greater than 1, so all your partial derivatives, or at least some of them, are greater than 1, then you will run into the exploding gradient problem. So please note that you are not running into this problem because you have lots of layers. You are performing back propagation over time. You are performing forward propagation over time. The vanishing gradient or exploding gradient problem you are encountering not because you have many layers. That's important. This point is very important. The vanishing gradient or exploding gradient problem you are encountering not because you have many layers, but because you have sequences. Your sequences are long, and your input, the one word after the other, that's the problem. This problem is major issue. This is a major issue for recurrence neural networks, RNNs. There are modifications for simple RNNs. What we have seen till now is simple RNN. There are modifications to simple RNNs called LSTMs and GREs. These are special. I can say these are special RNNs which will avoid the vanishing gradient problem or exploding gradient problem, isn't it? So these structures, LSTMs and GRUs, are super important. These are specialized RNNs. These are special purpose recurrent neural networks. I request you to go through this lecture once or twice. If you have any difficulty, please keep a comment. Thank you very much. My sincere request is, before understanding this lecture, please refer backward propagation, the training of multi-layer perceptron, which we discussed few lectures back. Thank you very much.